Well, I think we can start, folks. Welcome back, everyone. So for today's class, my main goal is really just to finish up section 10.5. We have a problem where we just have to make a conclusion and then a whole brand new problem to get through. But it's good to get extra practice on this since, as we see on the chalkboard and as we saw in the notes, there's really three different formulas for calculating your p-value, given your hypothesis test. If we have a left tail test, if that chalkboard is not too readable, let's scroll up right over here. If we're dealing with a left tail test, then we just take our test statistic z, whatever it comes out as, it could be positive or negative, and just find the area to the left. So we're really just doing a section 6.5 type of problem whenever we're coming up with the p-value. But we have to come up with this right here in the alternative hypothesis if we're really doing a left tail test. Likewise, on a right tail test, we take the area to the right of the test statistic z, and the two tail test, this one is a little bit special. It splits itself into two different cases. If your test statistic is positive, we double this area since it's two-tailed. If it's negative, we double that area. Really, we're just taking a shortcut, so we don't have to calculate the probability of that area. And then another area here, which would have been exactly the same. We save a little bit of time just writing it out that way, but it does make it a little bit harder to visualize when you see it as a graph there. Any questions at all, folks, with any one of those three different cases? Okay, well, with all that information, this is a good spot to come back to. I'd say for the final exam, something kind of condensed based off this would be a good idea. And then coming down here, I think we're doing a problem with teenage driving and texting, just to remind ourselves of the context. Yeah, go ahead. You know, I was actually going to change that a little bit. I've kind of gone backwards and forwards, but I felt like now that you mention it, for our final exam, 2 pages of notes probably does make sense. There is a lot of formulas in this class. I mean, just hypothesis testing alone, I've taken up half the chalkboard right there. So let me make a quick note of that. And I'm going to make a lot of that information more official once we're over the break. I'll be filling out this with definite information, review material, and what you mentioned about the notes as well. So we'll go for 2 pages of notes, front and back, whatever you'd like on it. It could be handwritten, typed out, and machine printed, completely up to you. But let me write this down so I don't forget and then get confused on the final. Little notepad is actually getting a little bit thin. We've used quite a lot of these. Okay, thanks for mentioning that. Other questions at the moment? Okay, so back to this problem here. We're dealing with P. We're trying to do a test on this. P itself was the true proportion of all 16 to 17-year-olds. And this is can't be globally. I believe this is probably United States of America based off some of the information I see here. Oh, it says Americans. So more than likely, we're talking about the United States of America. So American teens, age 16 to 17 years old, that indicated they had sent a text while driving. So the null hypothesis is that that should be at 0.25, so 1/4 of them. And that's based off, let's see, a 2000, nope, that's just based off the question right here. Who knows where they got that value, 0.25? That's what they asked us, so that's what we tested. They want to know if we can find evidence that more than 1/4. So we formed a greater than sign here. And then after checking conditions, this is kind of the meat of the material right here, getting the test statistic out. If you can get the test statistic, everything else is really a section 6.5 problem. We just have to choose one of the right cases that matches. So the standard error is itself very, very tricky. Whatever is here in the null hypothesis is what conveys directly down. This is not p-hat, and it'll only be p-hat if we're doing a confidence interval procedure. So after putting that all together, we found it was 0.4460 standard deviations, that the sample data p-hat is away from the hypothesized value p-naught at 0.25. That's not very much. So once we go to calculate the p-value, we had a very large p-value. Here, let's double check. This was a right tail test because of that greater than sign. So we calculated this area to the right here. I found a p-value 0.3278. A p-value with a 0.3 right here is essentially always going to be failing to reject the null hypothesis. our significance levels alpha are usually as large as a 0.1. And so this is considered ginormous in the land of p-values. So here we get to write down this conclusion. We failed to reject the null hypothesis, but maybe better said, or in our organizing thought here in orange, let's say this another way. We do not have enough evidence to support HA. And that's essentially what our conclusion is going to be. We have to read out everything, what the parameter is, the directionality, and that kind of stuff. But this problem is another good reminder. We mentioned this quite a lot, but here's one of those situations where it's tempting to say, we found evidence that the proportion is 25%. That's not the case, so we have to avoid. Let's make just a warning statement here. We cannot conclude H naught is true in hypothesis testing. Which is, in one sense, one of the major disappointments of the procedure. There are times where that is the question that people want to ask. Hypothesis testing won't support that kind of question. And just a reminder, the logic about this is still like a court of law. We're assuming the null hypothesis is true, gathering data. Here's our evidence right here, and seeing if we have enough evidence to say that's unreasonable. We didn't find that evidence to say the null is unreasonable, but it doesn't mean we're supporting that. It doesn't mean that this is a true statement whatsoever. So back in part E, we'll say these data do not provide. Let's highlight this right here in yellow, does not provide because we did not have enough evidence to support the alternative, does not provide significant statistical evidence to support the claim that. Then we go back here and we're reading this out. We didn't have enough evidence to show that is true, which was the goal of hypothesis testing. So we go back over here, write out what P is, that the true, I'll go with a percentage, true percentage of all 16 to 17 year olds that indicated they sent a text while driving Okay, we got through that portion, and I have to be upfront with folks. That is a lot of copying. I apologize for that. That's a lot of handwriting. It's just right there. And the reason we are taking this kind of a redundant step is putting this down, if we never wrote down the parameter P in the first place, is definitely very tricky. More advanced classes in statistics might not have us do this step right here, but when we write our conclusion, it has to look like that. So that extra little tedium and extra writing is just so that we're on the right track before we even get started. We're heading towards the right direction. Sorry for the extra tedium. I'll try to make sure the exam problem doesn't have our parameter width is like a whole bunch of lines you have to write out. Well, it should be a little bit more quicker than this one. So we wrote out what P is, then we'll just say is greater than . And then I said percentage, so I'll go with 25%. I guess I'll go to black on that. So that's the full statement. It's a statement where we admit we just did not have the evidence to make that claim be supported. Well, we did it, folks. That's a full top to finish hypothesis test with the conclusion there. Any questions or comments at all with that conclusion? Okay, so if we fail to reject the null hypothesis and Our statement here just has to say does not provide evidence, or we did not show anything like that, and you're on the right track. If our p-value looked like this, suppose it was, I'll fix this in just a moment, 0.0032, then this is all we would have done. The data provide significant statistical evidence and all that statement there. Yeah, go ahead.
Is that where our definition of how we can determine, right? Oh, sorry.
Oh, right over here?
Yeah.
Yes, absolutely.
That's how we can determine if we reject or fail to reject this little table right here, right?
Exactly. So this is a very good table to always come back to. One way to think about this table is you want your p-value to be small, smaller than alpha, and then we reject that study. But now that you mentioned that, let's put this right in our problem just to tie that thought together. Thanks for asking about that.
That's where I'm having a hard time trying to figure out if I'm rejecting it or failing to reject it. But if I just refer to the table.
Then you're all set. Yeah, exactly. Absolutely. Other questions at the moment? Okay, just for emphasis on that, let's drop that table right over. I think it would go really good right before E, because once you calculate the p-value, that's when you're looking at the significance level alpha and deciding what is the decision, fail to reject or actually reject the null. So the table comes into play here. And in this problem, excuse me, we had this situation, a really, really large p-value, much larger than the 0.01 that was specified. Other questions or comments so far? Okay, so that's a complete study. Looks like we have a good about 38 minutes or so. We probably should be able to get through another problem, so let's give it a try. And here's our example 3. This one, it looks like it's really pretty serious data this time we're taking a look at. It says the report, A Crisis in Civic Education, American Council of Trustees and Alumni. This was a 2016 study, so it's getting a little bit older. And you can look it up if you like, it should be there, but that's a website, so it's probably gonna change a lot. It summarized data from a survey of representative sample of 1,000 adult Americans regarding their understanding of the US government. So already we have a sample, n equals 1,000 to start out. On the next portion, it says, only 459 of the adults in the sample were able to give a correct response to a question asking them to choose the correct definition of the Bill of Rights from a list of 5 possible answers. Here they're talking about the successes. If they give you a number relative to the sample, 459 adults in the sample, then that number is what's important to them. They're indicating successes right there. So let's say 459 successes. And that statement that's highlighted in gray is also describing what a success is. A success is, let's see here, being able to correctly identify the correct answer in a multiple choice quest or test what the Bill of Rights was. So that's less than 50%, and that's kind of concerning in a way, because when it comes to exams, multiple choice is just testing recognition. It's not the highest level of understanding, and so less than 50% were able to even recognize the Bill of Rights in a list of 5 possible choices. Next, they say, this looks like a command, determine if. Sometimes a question in a statement could be the alternative hypothesis, but other times a direct command, that might be the alternative hypothesis. Determine if there is convincing evidence that less than half of adult Americans, let's highlight that there, could identify the correct definition of the Bill of Rights. Well, there's a less than, so we definitely have some directionality. Looks like a left tail test. They said half of Americans, so this statement is really informationally dense right here. Let's break this down. When they say less than, we're doing a left tailed test. And they gave us even more. They gave us the value to be tested in the null hypothesis. Let me just try to circle that a little bit better. The value of P naught is inside there. And it's this quantity when they said half. So we're just going to put in 0.50. or 0.5, but 0.50 just seems more impressive. It makes me think of 50%. So we want to know if less than half of, now we're talking about all Americans in the United States of America, could identify the correct definition of the Bill of Rights. We'll use a 5% significance level, so that's probably highlight worthy as well. Or if I could find the highlighter key. From that statement, we can write out that alpha equals 0.05 in this problem. So that's the full rundown. We're going to test based off this real study right here. It was based on 2016, so the current present day information won't be exactly the same as what we see here. But we're going to see how many Americans, if it's potentially less than half of them, could correctly identify the Bill of Rights. Any questions at all, folks, before we start to delve further into this one? Okay, first thing we've got to do is definitely indicate the parameter. Population characteristic is our author's go-to word on that, using the context. Then right after that, state the null and alternative hypothesis. And by the way all these questions are formatted, this is really just a step-by-step guide of how to do any hypothesis test. If you did skip this first step right here, you would definitely do it in your conclusion. But you would have to state null and alternative. So let's write out P equals the true proportion of all Americans or USA citizens. Let's use their language and just say Americans for short. That can correctly identify the definition of the Bill of Rights. I did leave some stuff on there. I didn't mention how it was, let's see, correctly identify a response from a list of 5 possible answers. I didn't mention it was multiple choice with 5 answers, but we kind of conveyed that when we said correctly identify definition of the Bill of Rights. Any things folks would like to include or exclude so far from that parameter? Okay, we're happy with that. Then the next step goes immediately like this. Test H naught, where it's going to be a statement P equals 0.50. So that's our value to be tested coming from this quantity right here. So we'll test that null against this alternative statement, HA, that the parameter P. Here, we're doing a left tail test only because they said less than right up here. So we literally write in our less than as they requested, put in the value to be tested, 0.50. And then this will be at the alpha equals 0.05 significance level. So that's our full statement. You don't necessarily have to say test against at the significance level. You can just write out kind of like a skeleton. H naught, your HA, and your alpha value altogether would be just fine. Well, that's what we're going to test. Next thing we'll take a look at is if we even should test it, if the conditions are met on this thing. They tell us the sample was, let's see, representative. So that is good information we know. It does make me uncomfortable. I don't know how well it is representative, and that certainly means it wasn't randomly selected. This would be really bad if it was, say, 1,000 people out of a college university or something like that, because now we're not having something that represents all Americans. So there's a lot of worry when they say representative sample, but we're going to trust them and just go forward from that statement there. Here I'll just say the sample is representative of the population of all Americans, we hope, but that's what they told us. So we'll go on to the next statement. Now we have to calculate two things. If the null hypothesis is really true, we need to know how many successes to expect and how many failures to expect. Actually, this one's a really fast computation. The numbers are just sort of nice on this problem, but let's still write it out as if we're doing it by formula in case the numbers are not so nice. I would write out something like this. Expected successes, expected failures. And you can say here, just to convey the thought, when H naught is true. So when H naught is true, the expected successes would be the sample size n multiplied by the proportion 0.50. And if we write this out, this is just going to be 1,000 divided by 2, essentially, multiplied by 0.50. And so we have lots of successes, 500 of them, if the null hypothesis is true. That exceeds 10, so this condition here is met. Then over here, we can do the same thing, but usually I would have calculated it in this way. I would have taken the sample size minus the number of successes that we just found. This would turn into 1,000 minus 500, which is 500, again, greater than or equal to 10. And so we have definitely a large enough sample size. We're in pretty good shape on this thing. So overall, let's say here, the sample size is large enough and the conditions are met. So now we can have confidence in whatever conclusion we write, it's going to be a great conclusion, provided the sample was representative. That's always a worry, no matter how you look at that. Next thing we're going to take a look at is test statistic, then we'll get our p-value and a conclusion. But any questions or comments so far, folks, to this stage? Okay, it's a weird problem whenever you're doing a hypothesis test, because when you look at this, I mean, aside from n times 0.50, there's really no math at all in all of this. It's all just analysis of the original setup, indicating a parameter and testing hypotheses. But now once we go to test statistic, this is the more mathy portion of the whole thing. Information we're going to need is right up here. We need the sample size, number of successes. And we're also going to need the null and alternative hypothesis to calculate that test statistic. So we need quite a lot of information. Let's carry it down here and start cranking it out. If I get everything to kind of fit a little bit better, there we go. So for test statistic, first thing I would probably write down, this is really a pretty good strategy on exam. Just write down the formula so you can visualize better where everything goes as you plug in. So Z equals P hat minus P naught, and divide that whole thing by standard error of P hat. Next, we need to calculate some of these values, but we already have the value P naught right here. From the null hypothesis, that's the 0.50 value. So next thing on the line is P hat. We take number of successes, 459, divide by the sample size of 1,000. And ordinarily, we just plug this into the calculator, got a decimal place. I rounded these to 5 decimal places because I was being pretty careful. And you know what, in this problem, just for the sake of a different approach, let's leave it just like that. We're going to get the more accurate answer if we, well, you know, looking at this a little bit again, if we did divide, we would get an exact answer, 0.459. I forget the divisor is 1,000. So that one's good to just crank out and put it right here. What I was going to say is, if it's a fraction and you don't want to round it to 5 decimal places, sometimes it's okay to just put it right there in the calculator as a fraction like that. That way you're not worried about rounding errors and things like that. But no, in our problem, that's a pretty nice and exact answer. We'll use it in that form. Next on the line is standard error, p hat. This is a good one to start by just writing down the formula as well. It's square root. And then from the null hypothesis, we're assuming this is true. And then what we're calculating is going to be the true standard deviation of the sampling distribution of p hat. So we'll go p naught, 1 minus p naught in the numerator, and divide by sample size n. So yet one more of these computations. We're starting to run out of them. We're going to be doing numerical data after this section, but let's still be really careful. It's going to be a 0.5 right here. 1 minus 0.50 is still just 0.50. But I usually write out this just to show where things went when you look in the notes. That way, you're not sure what just happened there. So if you do take shortcuts and calculate things as you go, that's completely fine as well. Then sample size was exactly 1,000, which is going down here. And finally, we're ready to get our approximation. I'll go for 5 decimal places and just round the final answer z down to 4. So we have second square root to start it out, then 0.50, 1 minus 0.50, divide by 1,000, and that's our quantity there for standard error. I've got a 0.01581. Does that look all right to folks so far? Great, let's put that in, 0.01581. So after all this preparatory work on the margin to the right, we just plug everything back in. We're just about to get our test statistic z. So z is measuring the standard deviations of your actual data against our hypothesized value of what the parameter p should have equaled. So it's going to be equal to 0.459 minus 0.50. And note, those look close, right? It's off by 1,000, but that's never the full story. We have to bring in the variability, and that's the standard error. It's 0.01581. Now back to the calculator, we just need to figure out this whole quantity. Doesn't want to expand over there for some reason. Let's just go like that. So next thing, I'll put parentheses around the numerator to make sure we're following order of operations and capture that whole statement, 0.459. And oh, that's off by a little bit more than I thought. That's off by about, say, almost 4.1%. Some reason I looked at that and thought those numbers were close. I think the 9 there just threw me off. So minus 0.50. And here's our next trick. If this is on paper, you definitely get partial credit, but in the calculator, I'd probably just go division, second, the negative sign or the up arrow. So that way we're putting in this entire thing in its exact form. And in fact, the calculator is not even rounding this. What the calculator is using on this line, when it refers to A and S, is this right here. It does the computation from scratch. And then it's just giving you the digits here. There's no actual rounding. So we have, let's see, to 4 decimal places, our test statistic z is negative 2.5931 after rounding. And that's a lot of standard deviations. It's getting close to about 3 standard deviations that p hat, our data, is away from the null hypothesis statement. So we are almost assuredly at this stage rejecting the null hypothesis. Unless that was pretty small, like say a 0.01, I would really have to calculate the p-value to be sure. We still need to calculate the p-value to show the degree which we rejected the null. And so let me get a new screenshot for the next step. Any questions at all, folks, on our z test statistic? Okay, now next up is the p-value. When you're calculating the p-value, the very first thing you should take a look at again is your statement of your alternative hypothesis right here. But let's carry all of part A in. So first thing we should do is just to organize our thoughts, let's recall that this is a left-tailed test. So let's start with the picture then. In the left-tailed test, we're going to be shading area to the left. But we have to know what quantity are we shading to the left from. The answer to that is it's all about the test statistic. It's going to be the cut point on the normal distribution here. But let's fill in U is 0, sigma is 1. And let's get let's just highlight in yellow. That ought to work. Let's take this Z here. It's almost 3 standard deviations away, so somewhere in this region. Well, let me try better. So this would be about 1, 2, somewhere around here. Doesn't have to be perfectly placed, but it just feels off if it's in a weird spot. The Z is negative 2.5. Let me try again. Z equal negative 2.5931. So now with this picture here and the shading, this implies that the p-value will be the probability that X is less in the left tail test, the Z test statistic, negative 2.5931. So we're at that stage where the whole problem right now is a section 6.5 problem. We're calculating that area using the normal distribution. So now it's a normal CDF type of process. Any questions before we put these in? Okay, well, one thing I usually do is put in these inputs. Input number 1, because we're shading to the left, non-stopping, is negative 10 power 99. Input number 2 is the test statistic Z. And in a hypothesis test, either input 1 or 2 will be that Z test statistic. These are the last two, 3 and 4, but they stay as 0 and 1 always for p-values. And now we're in good shape. So let's hit second bars. Go to normal CDF. Our lower looks correct. I mean, that's their version of 10 power 99. It just looks weird. If you want it to look the same, no harm in rewriting it. You get the same quantity either way. Upper value is negative 2.5931. Then 0 and 1 for our parameter values. And all that gives us a p-value of 0.0048. Barely rounds up on this one. Anyone getting something different, or is this coming out okay so far? Okay, let's grab this value, 0.0048 altogether. Let me double check that I got that in correctly. Okay, so we did it, folks. That's finally our p-value. Next, although we don't have to do this right away, sometimes right here on part D, it's a good time to organize our thoughts even more before part E and decide what will happen. So, and I kind of hid what we need to look at. We take a look at our p-value, compare it against the significance level alpha, and we have to make a decision. Will we reject the null or will we fail to reject the null in this one? Can anyone tell? Exactly. Here we're rejecting because this number is much, much less than the alpha value right here. But again, these are tricky problems, so let's throw this in just to connect that thought. So here's our situation with 0.0048, rather. We can say p-value equals 0.0048 is less than, then the thing that we want it to be less than is this alpha value right here. And it's true, it's much less than it, 0.05, which is equal to alpha. And that means we're not in this situation. We are in this situation. We're going to reject the null hypothesis. So here we go. It's gone. And we this time found evidence that that statement is true. So we're going to support it by just writing that out as a conclusion. Any questions at all, folks, so far? Okay, we're nearly done with the analysis, so let's just write out that conclusion. We'll say here, we have found, this is kind of a slightly depressing conclusion, but it's good information. We have found significant statistical evidence that, now we go over here after writing that out, and I forgot to highlight that in blue, that the true proportion of all Americans that can correctly identify the definition of the Bill of Rights. I forgot to Google that before class today just to refresh myself personally, so I fear I might be in the wrong end of this kind of problem as well. The definition of the Bill of Rights then we come here, take a look at the inequality. Literally, we just get to say is less than. And this time I said proportion, so I'll stick with proportion and put in 0.50. If you went with percentage, you would just go and say 50% here. Or you could just say less than half. That's completely fine as well, using just ordinary language. Well, we did it, folks. That's the end conclusion on this thing. And this study was a pretty serious study. They would have gotten the same conclusion that we have gotten. And the conclusion of the study might have caused some action, maybe in like the K through 12 schooling system. Maybe government classes should just have a little bit more drive on certain content. Might have been their conclusion and recommendation. But this is a pretty high stakes study because being unaware of these kind of civic information just is not good for democracies, makes us pretty vulnerable to propaganda. So that's probably why they started the study in the first place. They were suspicious that might have been the case even before they collected data. Well, we did it, folks. That's the conclusion of hypothesis testing. Congratulations. I think chapter 10 isn't the hardest chapter. In my opinion, let me know if you change your mind on that or have a differing opinion. I think chapter 5 is the harder chapter in this course. When it comes on the final exam, I'm only going to put in a couple of the routine questions. The whole purpose of chapter 5 is to take these kinds of things, which are probabilistic statements, and interpret them. So chapter 5 isn't going to have a heavy presence on the final exam. As far as it's going to be cumulative. I'll have one conference interval procedure and one hypothesis test procedure. And I'm going to use a random number to decide, will the hypothesis test be like this one with categorical data, P, or will it be with numerical data, mu there instead? So that's what we're going to take a look at next. We're going to look at conference intervals again and hypothesis testing, but this time with numerical data. We'll ask questions, is there evidence that the average height of Americans is less than some quantity here? That'll be the nature of the new problems. Any questions before we take a look at those notes? Okay, let's close this up. And the last thing I want to do today is talk about the sampling distribution one more time. We'll refresh ourselves on that when we come back after the break. But it's such an abstract topic, and it's the complete backbone of all of our inferential statistical methods. It's a good idea to take a look at it just one more time. So we were all the way back in section 8.2 when we did our first sampling distribution, but we're about to do it again. In section 12.1, we're looking at means for numerical data, so we need the sampling distribution of the mean. Here's the picture from back in the day. When we go and grab a statistic, say p hat, we're really grabbing that statistic from a whole new probability distribution. Under the right conditions, that probability distribution looks about like this. It's normally distributed, and so p hat comes from somewhere over here. This information led us to the central limit theorem, and so we're going to rewrite this theorem, and the only difference is you won't see a P here, you'll see stuff like mu. So here's what it looks like. We're not going to try to get too far on these notes, but here they are. First, it's a reminder of some of the definitions. Population is everyone we're interested in. Sample is just going to be a small selection. And if we say population characteristic or parameter, if I slip up, we're talking about something that describes a population. And if we say statistic, then we're talking about something that describes just the sample. So we have many different kinds of statistics, X bar and S. And over here, oh, this is a screenshot. I can't draw on this thing. Over here, X bar estimates mu, S estimates sigma. And here's what the sampling distribution looks like and the process that it comes in from. We'll have a population that is numeric. So there's going to be a population mean mu, population standard deviation sigma. And if you do one study, here's the visualization. Our author uses Y bar. The author here, I mean, rather, this came from a different textbook. I just thought it was a great screenshot, so I stole it and cited it. Think of Y bar as X bar, and we're doing really the same thing. So we have a population. This refers to a random sample. And these are the statistics you would calculate. And what we're putting in is that one Y bar comes down here, and we can place it on a histogram in this way. Now we imagine the abstract thought of replicate this study. We keep on doing this, we get different values of the sample mean because we have a different sample, all of them of the same exact size. So this sample mean Y bar or X bar if you prefer, it's a little bit different, it moves to a different spot. And we keep on imagining replicate this over and over until we have all possible values of X bar that could ever emerge. When you do that, you can collect all these values into a histogram, and this is the shape that comes up once again. It looks like it's very clearly a normal curve. Our goal now is to decide what are the parameters of that normal curve? What are its population characteristics? And this is the content of the central limit theorem. The average, which is going to be right here, mu, of X bar, is the true mean of the population mu itself. So every time we gather a statistic, the center of where that statistic came from is close to the thing we really want to estimate. That's good. It tells us our statistic isn't biased in one direction or another. It's an unbiased estimator. Then, again, that's great information, but it's never, ever the full story having a mean. We can't do anything with that. We need to describe variability. And the variability on this thing is going to be sigma of X bar. That looks weird to say sigma of X bar, but we're saying the standard deviation of the sampling distribution of X bar in that one symbol. This is going to be sigma over the square root of n. That's our new standard deviation. It's unfortunate though, because we won't know the value of sigma. And so we do something else. We take the fact that S itself is approximately sigma. Oh, didn't mean to close that. This sigma here is truly unknown because it's a population characteristic. Our whole goal is to estimate these things. So back over here, like we're saying, the central limit theorem is useless unless you know the variability. Variability is unknown though, so we're back to square one. We're kind of stuck. But there's a fix, and the fix is called standard error. We'll write out a new standard error. It'll be the standard error for X bar, or we could say the standard error of X bar when you see that. The parentheses aren't indicating multiplication, it's just saying which standard error this time. We come up here, we're going to use the estimate and swap that out and put S over the square root of n. So that's our estimate of the variability on this new normal distribution. So that's the content of our brand new procedure. All we need to do is adapt the new standard error to our formulas. And you know what? It's pretty quick. Here's the last thought for the day. Then we'll call it a vacation or a quick holiday. In section 9.3, we went p hat plus or minus z star times the standard error of p hat. Whole formula for that standard error. In section 12 point, I think this is 2, we're going to go X bar Why X bar? It's because it estimates mu really well. Add or subtract? This is the difficult part. T star. We need a slightly different distribution, which is highly similar to the normal distribution, but it's not exactly the same. So that's why there's an extra section before we look at the confidence interval. And then we just multiply that by the standard error of X bar, which is this once again. So the procedure for the confidence interval looks almost identical. This is the only adjustment we'll have to make. So that's where we're going. Any questions about this diagram so far? Yeah.
So there's like, depending on what we're doing, there's 3 different equations for standard error. Right?
There is, yes. There's standard error p hat in a confidence interval, standard error p hat if we're doing a hypothesis test, and now standard error of X bar whenever we're dealing with numerical data. So that's a crazy symbol, and that's why I like to add the little extra designation, whether it's dealing with p hat, one formula, or X bar, a whole different formula. Other questions about that so far? Okay, good news is the formula is fast. It's really nice. We did the harder formula up here. It's a lot harder. The bad news is we need a different probability distribution to get our critical number. But that's part of the reason why we have all these extra days to finish off 12.1 and move to 12.2. Well, I think that's pretty much all I have for folks today. Any last questions, comments, thoughts, or concerns? Okay, well, have a wonderful holiday, folks. If you're working over this holiday, I'm still available by email, so don't hesitate to write. Otherwise, I'll see you all in, let's see here, this is going to be, wow, the 27th, right before December. Take care, folks. Be safe, and I'll see you all on the 27th. Here you go, Ricardo. Let's work on that. Thank you.
I had that one WebAssign problem I was having trouble with. I thought at first I messed up the sample size, but I think I did that right. I think I'm having a problem with the part B. I don't have my computer to show you, but
Yeah.
I'm thinking I'm having a problem with the part B null hypothesis sample.
Gotcha.
Because it's like 1/3 instead of a decimal.
Oh, yeah, I remember that one. Yeah.
Yeah.
So
I wonder if I'm messing it up because of that.
it's possible. Yeah. One thing I would suggest if you're ever dealing with, say, a 1/3 is you have 2 approaches. You can either try putting in something like 0.33333, and that's probably going to be pretty safe.
That's what I tried. It didn't work.
It didn't work.
That's-
Another thing
that's
that
what
could
my
have happened
problem was.
this. Double check in your calculator. I know we don't have it with you today, but it's possible that something like this happened. Let me put in like, let's go. No, I want that to be, trying to think of the picture in my head is not always efficient.
I think that was the one that had the E, that you had to move the decimal for 10 places.
Yeah, that's what I was trying to get the calculator here to show, but it had it to 0 on this one. It went a
I
little
always
too
have a
crazy.
weird reaction with those ones, but I didn't get that kind of answer for this one.
Oh, I see, I see.
I had a different problem that had that kind of thing, but I kind of knew from past experience that it was a 0, 0, 1. This one was not that kind of situation,
Gotcha.
unfortunately.
It might be something else kind of small inside there, but I think I remember when you asked that question there.
Yeah.
I can take another look at it for you
Okay,
and email you after I take a look at that.
all
Does that
right,
sound all right?
thank you.
Awesome. Yep, you betcha. This was section 10.5, right? 10.5, gotcha. I did change the number of tenths on that. I was trying to give like essentially infinite attempts on these, and I just saved it and changed those attempts. Mhm. Hello.